Hello, my name is Trevor Ablett, and I'm presenting efficient imitation without demonstrations via value-penalized auxiliary control from examples. We consider example-based control as an alternative to inverse reinforcement learning. EBC is akin to sparse reward reinforcement learning, but with expert data. Examples are easier to acquire and less biased than full trajectories, but EBC can suffer from sample inefficiency and deceptive rewards. These videos all show policies learned via state-of-the-art EBC, and all are stuck in local optimums. Our main experimental question is then, is it possible to learn policies efficiently given only example states of completed tasks? To improve exploration in EBC, we can apply our previous work, learning from guided play. LFGP used full trajectories of auxiliary expert tasks to learn multiple policies, using a scheduler during training to improve exploration. We apply LFGP to the example-based domain in what we call auxiliary control from examples, which does, in fact, improve exploration. However, it introduces a new problem, where highly exploratory data causes overestimated value functions that break learning. Take a look at this example of this overestimation problem. Here, a partially learned agent learns Q values for arbitrary motion that are much higher than Q values for successful states. To prevent this scenario, our goal is to keep Q values less than or equal to Q values of expert successful states. We can enforce our goal as a quadratic penalty whenever Q estimates go above the max value. Now our policy will correctly learn to avoid unsuccessful states. Here we show our setup for our real-world experiments. The images on the right show samples from the initial state distribution, as well as samples of the example states used for training our real-world door and drawer tasks. Notice how much easier these are to collect than demonstrations, where each set of states is collected within seconds. Note also that these are not stuttering videos, but rather a slideshow of the static successful examples used for training. Experiments were completed in 4 environments, with example tasks shown in the bottom left, with 21 tasks in total. We considered 3 single-task inverse reinforcement learning baselines, one of which was designed specifically for the example-based setting. We also included R&D, an exploration novelty bonus, showing that providing bias on how to explore is necessary for the best performance. VPace improves performance in all tasks, but value penalization makes a bigger difference in the harder SimPanda tasks, which we hypothesize is because they are longer horizon and have a larger observation space. Importantly, VP never harms performance. Here, each video shows an exploratory policy at 40 minutes, 2 hours, and then a little over 3 hours. The left columns show task switching in real time, while the right columns show time lapses over 4 minutes total. The exploration here is shown as reach, grasp, main, but the actual exploration policy sampled both handcrafted high-level trajectories like these and random combinations. SQIL, the highest performing baseline, fails to learn the task. Here are the same comparisons at 2 hours, where VPace has now started to learn the task. And again at a little over 3 hours, where VPace has successfully learned the task. This is the final performance of the main task, without executing any auxiliary task, showing that the main task subsumes the auxiliary tasks. In conclusion, our experiments with VPace showed that better expert data may be more important than simply adding more. In our case, we're talking about auxiliary tasks and examples instead of trajectories. Auxiliary tasks may not always be trivial to choose. However, in this work, we used exclusively reach, grasp, lift, and release for all 21 tasks. We also get better performance than reinforcement learning with exclusively sparse rewards and inverse reinforcement learning with full trajectories, which you can see in our poster or our paper. Next steps include investigating automated task discovery, automated scheduling, or applying our framework to offline RL to warm start policies. Thank you.